Okay, it's setting up. Good. We are on YouTube now.
Yeah. Okay, great. So good morning, good afternoon, and good evening, everyone. So today it's our great pleasure to have Dr. Daniel Fagihi to join us and give us a great presentation. So the title of his talk is Validation and the Selection of Predictive Computational Model Under Uncertainty. And Daniel is currently an assistant professor in the Department of Mechanical and Aerospace Engineering and holds an affiliated position at the Department of Civil, Structural, and Environmental Engineering, as well as the Institution of Computational and Data Science at the University at Buffalo. So before joining UB in 2019, he was a research scientist in the Olden Institute for Computational Engineering and Science at the University of Texas at Austin. So he obtained his PhD in structural engineering and mechanics from Louisiana State University. And Daniel's research interests focus on predictive multi-scale modeling of complex material and biological systems. In particular, he's interested in developing novel computational frameworks at the interface of physics-based models, scientific machine learning method, and high-performance computing. So Daniel is also the recipient of the National Science Foundation Career Award in 2022. So congratulations on that. And he has published more than 32 journal articles in the area of computational mechanics. So now let's welcome Dr. Daniel Fagihi to start his presentation. And now the screen is yours. Daniel, please feel free to share your screen and then you can start.
Thank you very much. I hope you can see my screen. Is that okay?
Yes, everything is good. We can see your screen.
Okay, thank you very much for the kind introduction. Before I start, I want to sincerely thank the organizer of CFSM seminar series for the kind invitation and the audience for attending this virtual seminar. My name is Daniel Fagihi. I'm from University at Buffalo, and I'm going to talk about validation and selection of predictive computational models under uncertainties. These are some of the works of my current PhD students over the last 2-3 years, Jingye Tan and Baoshan Liang, and some of the work of my master students, Pratyush and Shayan, and in collaboration with different scientists in San Diego National Lab, Washington, St. Louis, UT Austin, and University at Buffalo. So the motivation of this talk, and in general, the goal of my research lab, is making computational prediction of complex physical phenomena or complex physical systems. We now have a tremendous opportunities to harness large-scale data from either measurements, imaging, or high-fidelity simulations and integrate those with mechanistic models of physical systems to enhance their predictive capabilities. Reliable computational prediction allows us to make high consequence and often life and death decisions. A few examples are provided here on predicting the complex cell dynamics in various microenvironments using agent-based model and microscopy measurements, using atomistic or molecular dynamics as the source of data to inform continuum model to enhance semiconductor nanomanufacturing, leveraging MRI-based tumor prediction for personalized cancer treatment, and finally, design of high-performance insulation materials and components using predictive models. In all these applications and similar complex systems, the essential factor is the validation of the model in presence of data and model uncertainty, and how we acquire the validation data to validate our model that enable us to make computational prediction of the phenomena that we don't directly observe. For example, in tumor modeling, we want to predict the future development of tumor and then use that for decision making for personalized treatment. So one major challenge in model validation is the choice of model itself among all possible models that can be constructed for a particular phenomena. Take into account a simple example of coarse graining of atomistic systems by lumping some of the atoms into a single bead to reduce the degree of freedom. There are many ways that we can construct a coarse grain model from a single atomistic systems. For example, different degree of coarse graining, how many atoms needs to be lumped into a single bead. And for each of these cases, how many interatomic potential we need to engage into our coarse grain model, leading to large family of coarse grain models with different fidelity and complexity. Another example is continuum mechanics based models that the ingredients are basic physical laws, Balanced law of mass, momentum, energy, and so on, that we consider those to be reliable. Then we need constitutive equations that comes based on our simplifying assumption and bring inadequacy into our modeling approach. There are still many ways for a particular class of body undergoing a specific process. We can construct different constitutive equation that satisfy the second law of thermodynamics. So this leads to large family of mechanistic models with different fidelity and complexity. And the question here is that which one we need to use for making computational prediction. The domain scientist makes the modeling choice based on their extensive experience on the particular phenomena. While those experience can be leveraged, if our goal is to make reliable prediction, then we need a systematic approach to select the model that we use for prediction. These motivations brings me to the outline of my presentation today. I start with some preliminaries on Bayesian inference, model validation, and plausibility. And then I discuss a strategy for selecting optimal predictive model in the context of multi-scale plasticity. And then I provide an example of leveraging validated and selected model for predicting heterogeneous tumor morphology in a specific subject. And if the time permits, I discuss a little bit about our future work on neural net selections based on a given data. So let's start with some preliminaries. Consider a set of parametric models. As a script M, consists of model M1 to model MP. Each of them depends on a set of parameters, θ1 to θp. Vector of parameters that I'm showing here with the vector of theta. Now, in order to calibrate the model given observational data D, we can use Bayes' theorem to account for the uncertainty in data and model. It starts with a prior probability distribution on the parameters, and we need a likelihood function that's basically constructed from a noise model assumption and account for the distance between model and observational data. And the denominator of Bayes' rule is a probability of observing that particular set of data. And basically grinding these three probability distribution into Bayes' formula, we obtain our posterior distribution of the parameters given data, calibrated parameter after observing the data D. Now here I'm writing the Bayes' rule by acknowledging that these probabilities condition on the choice of the model set, and the scenario in which the problem is posed. For example, domain and certain boundary condition. These are important for our discussion in terms of model selection. Now the value or point estimate that maximizes this posterior, we know it as map. That's just a single value, it's not a distribution. And the denominator of the Bayes' rule is evidence. That is basically, we usually look at it as a normalization factor, but there are more into it, and I discuss that shortly. All right, so the way that we can inform the model by data to predict a particular quantity of interest is conceptualized as a prediction pyramid with different levels in the calibration that we have calibration scenario and corresponding calibration data, moving up to validation, and until we can predict the quantity of interest in the prediction scenario SP. In a Bayesian setting, we start with a prior on the parameters. We update that prior with calibration data to obtain the posterior, calibration posterior. We use that calibration with a new set of data. We know it as validation data. And again, update the parameter to obtain the validation posterior. Now we do our validation test, which means that we compare the model output with the validation data. And if it is less than a tolerance, then we deem the model to be valid. And only then we are allowed to use that model for making prediction of the quantity of interest in the prediction scenario. So this needs to be done for all the models in that model set, but the denominator of the Bayes rule is known as evidence, and usually people look at it as a normalization factor. But there are very nice features associated with evidence. Basically, in a very simple example, if we have one parameter, our prior is very wide distributed and the posterior is sharp round map, then the evidence can be seen to be a trade-off between how much the model can fit the data and how much information gain about the parameter from data. Obviously, these are both features that we want to maximize. Therefore, for model selection, we can write another set of Bayes theorem. This time, by having a prior on the model itself, we use the evidence as a likelihood function to obtain the posterior model plausibility. And in a set of competing models for a given data, the model with largest posterior plausibility is deemed the most probable model, basically the model that we need to use for that particular set of data. Okay, so these preliminaries brings me to first subjects on selecting the optimal predictive model in the context of multi-scale plasticity. The problem of interest here is sequential discrete dislocation dynamics to strain gradient plasticity. Discrete dislocation, we know that it's a high fidelity model, accounts for the evolution of defects and dislocation leading to plastic deformation, but it's computationally expensive, limited to length and time scales and regular domain. On the other hand, strain gradient plasticity account for the size effect in small scale and polycrystalline system and allow us to model large scale engineering system, basically. In particular, in this project, our prediction scenario is a MEM-based pressure sensor. The device is basically a capacitor in which the deformation of the top layer, the thin film at the top, changes capacitance and provide a measure of the applied load at the top. So the target prediction or quantity of interest here is how much this thin film is deformed under certain applied load. All right, in the context of a strain gradient plasticity, here we use a model that I developed over the course of my PhD. It consists of the classical Microforce Balance, consists of Cauchy stress, linear elasticity, combined with a Microforce Balance that include two macro stresses, accounting for basically upscaling some of the dislocation mechanism into continuum level. Upon plugging the constitutive equations, the Microforce Balance becomes another PDE that needs to be solved with the classical Microforce Balance. It requires mixed finite element for discretizing plastic strain and deformation. We need to be careful about compatibility of discretization and basically the small time step in Newton solver and so on to basically solve this system. This includes a bunch of model parameters. The important ones are energetic and dissipative length scale that give rise to size effect with respect to kinematic hardening, and flow stress in the stress-strain results of the strain gradient plasticity. All right, so now let's look back into our model. The Microforce Balance consists of 4 different terms, basically coming from those macro stresses. And back in the day, there was some disagreement in the community. Some models include only the back stress, the size effect due to the back stress. And some other group, they believe that this term is not really important, and the size effect is mainly a dissipative process. Although the community has been converged over the last couple of years, we take a model agnostic approach in this project. Basically, by turning on and off different constitutive equations or different terms in our model, we construct a set of submodels with different number of parameters, different possibly complexity and fidelity, and then we use the discrete dislocation simulation as observational data to validate and select the model that we want to use for prediction. So in the context of following the prediction pyramid, these are the scenarios that we are using for our calibration and validation. Basically, the data coming from a thin film simulated by discrete dislocations with different grain size, different film thickness, and the data are size-dependent stress strain. Our model basically are 2D strain gradient plasticity, and our prediction scenario, as I discussed, is this pressure sensor, polycrystalline pressure sensor that we don't have direct observation, and we want to predict the quantity of interest. And the question is, what strain gradient plasticity among that set that we develop we should use for making those predictions? We rely on Occam-Razor principle in this context that basically says among competing theories, we need to pick the simplest one. We translate this for selecting the optimal predicting model. And we say when choosing among the set of models, M1 to MP, the optimal choice is the simplest valid model. Basically, the simplicity coming from a measure of model complexity, it's subjective measure. Here we are considering the number of uncertain parameters. Validity is basically passing the Bayesian validation test, and we ensure the predictive ability of the model by design of model-specific validation experiment that provides the validation data that reflects the structure of target quantity of interest. Basically, we advocate that instead of just picking any data for model validation, we should actually carefully design the validation experiment for a particular model to be effective and enhance and improve the predictive ability of that model. Okay, combination of these with posterior model plausibility leads to a strategy for model selection that we call it Occam plausibility algorithm, or OPAL. The strategy is shown in this diagram. We start with a set of possible models, M1 to MP. We first do global sensitivity analysis just to see if we can do some of the parameters can be insensitive and can be assumed to be deterministic or fixed to reduce the computational cost. And then we categorize the models in Occam categories based on the level of complexity. Here, number of uncertain parameters. All right, having the category of the models, we use a bottom-up approach. We start with the first category, the most simplest models. And we do the Bayesian calibration and compute the plausibility of all the models in that subset. And we pick the most plausible model in that category to subject that to model validation. Before doing the validation, we confirm the validation experiment is providing data that is adequately informing that most plausible model of the prediction of quantity of interest through an experimental design process that I describe shortly. And if the most plausible model in that category passes the validation test, then we have our optimal predictive model. Otherwise, we need to go to the next category. We go through the same process until we hit the validated model. If no model is valid in that set, then we need to extend that set or acquire additional calibration data and do the process again. So I do a quick demo of Opal here in our multi-scale modeling approach. We start with global sensitivity analysis of the full model, M7. It turns out that Poisson ratio is not really sensitive, and we assume that to be deterministic. The rest of the parameters are basically uncertain, and we do them in a Bayesian sense and probability distribution function. We categorize the model based on their number of parameters. We have 3 categories, of basically 4 categories, that the last one is our full model. Then we start with the Occam step. First category, both of them has 3 parameters. Only difference is the term in the energetic or dissipative part of the gradient plasticity. We can do the Bayesian calibration and computing model plausibility. It turns out that M2 is the most plausible model in that category. Then we go to design of validation scenario specifically for this model. Here we come up with a simple example that our design variable is the amount of applied strain to the discrete dislocation dynamics that leads to the stress strain data. And we come up with 3 different possible scenarios for validation, S1, SV2, and SV3. And I remind you that our quantity of interest, the one that we want to actually predict, is the deformation of this pressure sensor. Now, the way that we do the design of experiment is by doing the sensitivity analysis. We do the sensitivity of this proposed validation scenario for model output set to the validation observable. And here would be the strain energy because it reflects the stress strain behavior. And we also do the sensitivity of the prediction scenario for the model output set to quantity of interest. And from the results here, it turns out that only sensitivity of the parameter in SV2, the red ones, are in the range or higher than the ones in prediction scenario, the one in the black. And thus, only among these 3 possible validation scenario, only the second one is an effective validation experiment that provide the data that inform the important model parameters for predicting the quantity of interest. Now, having the validation scenario determined, we recalibrate model M2 against validation data from obtained from this scenario, again using Bayesian approach. These are the posterior, basically calibration prior, calibration posterior, and validation posterior of the parameters and the hyperparameter M. And then we do the validation test by checking the validation matrix, basically the distance between the validation data and what is coming out of our model using the validated parameter. And it turns out that the distance or DKL distance is less than is greater than a tolerance that we pick in the beginning, and thus M2 is not a valid model. So we need to do the same process in the next level, in the next Occam category. And it turns out that actually in the second category, M4, is the validation matrix is less than a tolerance, which is 0.1, and we can deem M4 to be our optimal predictive strain gradient plasticity for this particular set of data that we are considering in this work. Basically, we need to terminate Opal at this point. We don't need to check other models because this problem here, we have only 3 models left. We actually did the rest of them in terms of calibration validation, and we can see that M6 and M7, both of them are valid models. They passes the validation test. However, the predictability of model M4 still is better than these two cases, because this particular model matches its corresponding data better. So now, having the optimal predictive strain gradient plasticity, we can do our computational prediction of the MEMS pressure sensor. Here is the evolution of plastic strain, accumulated plastic strain in the domain using map of the parameters, and then we compute the quantity of interest. That was the target of our prediction. All the parameters are stochastic, and the quantity of interest would be another distribution function with its certain credible interval. So in this problem, we didn't have lots of prior knowledge about the parameters because strain gradient plasticity hasn't been calibrated or integrated with data as much because of the computational complexity that is associated with it. But the good point about this project was that we had lots of data, because the data coming from high fidelity simulation, we could do our simulations. Next, I provide you an example of a problem that we have only a little data for making an important prediction that makes constructing the parameter priors to be extremely important for having a reliable prediction. So the overall idea here is using historical cancer data, for example, the data that observed and stored in several data sets for glioma and brain tumor, and leverage those to develop a predictive tumor model and use that for optimizing treatment in a new patient, in a patient-specific sense. Two important factors in personalized cancer treatments are, first of all, we need to be able to predict the tumor shape, because it's very important in metastasis and conformal radiation therapy. And the second one is a time scale that requires in clinical setting. Once the cancer has been detected, then we don't have that much of time, and we need to make the treatment decisions very fast. Here we use a forward model that is usually used in biomedical engineering. It's very simple. It's a reaction diffusion equation for the evolution of tumor volume fraction. It consists of only two parameters, diffusion and proliferation rate. But to capture the subject-specific tumor shape based on the earlier time point data, we consider these parameters to be especially varied. So the parameter depends on the space, and basically they are parameter fields. To demonstrate the subject-specific tumor prediction, here we use glioma growth data in rat subjects, basically. And these are preclinical data. You know that MRI coming with the imaging of the slices of the brain, basically. At the top row shows the evolution of tumor for the 3D reconstruction of MRI. And the bottom row is just a central slice of the brain that shows the growth of a particular tumor in a particular subject here. All right. So how we integrate data and model? Again, we recite to Bayesian calibration and Bayesian inference. We have a prior likelihood and we compute the posterior. But note that now our parameter is a parameter field. And upon discretizing the model parameter with finite element mesh, we get our Bayesian inference to be to have high dimensional posterior. And we get into the curse of dimensionality, which means that the regular algorithm cannot handle this much of number of parameters. Again, for each of these finite element nodes, we have one parameter that needs to be determined in terms of probability distribution. So to overcome those challenges, we resort to a scalable Bayesian inference algorithm that is independent of the computational cost, is independent of number of parameters. We construct our prior based on the Gaussian random field. Now everything is especially varying. And it's based on a matter covariance kernel, consists of the prior mean and basically solving these stochastic partial differential equations for constructing this prior. These two parameters in matter covariance control the correlation length with, of the spatial correlation length of the parameters, as well as the prior variance. The likelihood function is a simple Gaussian additive noise, the difference between model output and what we observe from MRI data at each spatial point. And we have a hyperparameter that is sigma noise, accounting for the noise model. All right, the scalable algorithm in this case coming from Laplace approximation to the posterior, basically linearizing the posterior around map point using Taylor expansion of the log posterior. And at the end of the day, it boils down to posterior being normally distributed or being Gaussian, and the mean is the map of the parameter, and we have a posterior covariance. So basically, it boils down to computing these two values for each spatial point. So the map point can be obtained from deterministic inverse problem with the objective function including the negative log of posterior, including the likelihood and prior contribution. And we use an adjoint Bayesian exact Newton conjugate gradient algorithm that is again parameter independent. But the main challenge is computing this posterior covariance. And since the posterior is Gaussian, this can be written as the inverse of Hessian of negative log posterior. Or further, the contribution from Hessian of negative log likelihood and the one that's coming from the prior covariance. However, since the theta is high dimension, it's a parameter field, we discretize it, this Hessian matrix is huge. And it's not very, the computational cost for inverting this big Hessian matrix is completely prohibitive. Here we are exploiting a low rank structure in the parameter space that are well informed by data to approximate this, this basically big matrix and Hessian. In particular, upon solving the generalized eigenvalue problem based on prior precondition Hessian, the low dimensionality of the problem is revealed by rapid spectral decay of the Hessian. For example, here is shown the decay of eigenvalues for this problem based on their number of eigenvalues, and this decay is actually independent of the number of parameters. Here you can see that two different discretization, basically the eigenvalues are coincide with each other because they are only depends on the number of modes that are informed by data. And the posterior covariance then can be approximated by retaining only a number of dominant modes that are informed by data. And basically to provide an approximation for the posterior covariance. Now, having our method, let's go back to our tumor model. As we said, we want to predict the tumor only in a subject-specific sense, which means that using earlier time point to predict the future of tumor. So we don't have that much of data. And we construct here a subject-specific prior to bring other information into our inference problem. Basically, the brain heterogeneity and different mechanisms in gray and white matter that leads to irregular shape of the tumor. So gray and white matter cannot be distinguished from the imaging data of rats because the brain is very small. And we develop an atlas-based MRI segmentation of the brain using image processing and basically the deformation of the specific rat brain with respect to atlas to basically come up with the estimate of the region for gray and white matter in a specific rat. Then we use the historical data or previously calibrated model to construct the subject-specific prior with different prior means and correlation length in gray and white matter of a specific subject. So now we have all the ingredients. We have our prior, we have basically based on the subject specific, then we have our posterior that is relies on Laplace approximation. And let's see how it plays out in terms of predicting the tumor. So I'm just showing one rat here. The top row are the data volume fraction of tumor cellularity in the brain of the particular rat in the central slice, and the bottom row shows what is come out of the model. The first time point we use that for initializing the model as just initial condition. We use several time points, day 12, 14, 15, and 16, as our training set that is included into our Bayesian calibration, and we leave out one data point at the end. We call it testing set because that is an unseen data that we want to check our predictive ability. And you can see that our model, even though it doesn't see this data, it can capture pretty well the spatial distribution of the tumor through the domain, leveraging the previous data that coming from the previous time points. The map and point-wise variance of the two parameters now in the log space, log D and log G, are shown here. Basically, we can see that when they have data in this region, the point-wise variance reduces because the parameters are getting informed by data. A little bit about the scalable algorithm. Eigenvalue and eigenvectors for this particular rat are presented here. The dominated moods, but you can see that it covers large part of the domain where tumor resides, while the smaller eigenvalues leads to eigenvectors that only account for smaller length scales. Having this posterior covariance, then we can actually draw samples from our posterior parameters in a special manner. A couple of samples are shown here that accounts for the reliability in our prediction. So now let's see how reliable is our prediction, not only looking at the map of the parameters, but actually in the samples of the prediction. Here we are doing two cases. In both cases, we have our initial time point and testing time point the same. The difference is in case one, we use the 4 data points. In the case 2, we are doing only day 16 as our calibration time point. And we are checking the predictive ability of our model in the testing set, day 19. Case 1 shows the tumor boundary that is coming from data and 500 samples from the posterior that leads to possible boundary of basically tumor that is coming from our prediction. You can see that these samples are very close to our map point and very close to our data in case 1 that we use 4 data points. While the map of the parameter in case 2 is very close to the observed data, we can see that we have high uncertainty and low reliability in our prediction because the tumor boundary that coming from different samples are actually very spread throughout the domain, and they are not, the variance in our prediction is high. I just want to point out here that we are using actual MRI data, and there are many uncertainty associated with those data. So this testing set is not a ground truth, and the error that you can see here, some of them are associated with the image processing and how the data are acquired, basically. All right, so now we have this predictive capability. We can see that the reliability depends on how many data points that we use. And the next step in this project is to creating a cancer digital twin. Basically doing the inference in a dynamic sense while we are acquiring data. And basically, every time that we get an MRI from a new patient, obviously we are doing it on rat brain again, we update our model using a Bayesian filter and use those computational prediction to optimize the treatment with the objective of minimizing the tumor in future time. The posterior model plausibility can be very helpful here, in which instead of just again relying on one model, we can compute the plausibility of few validated model and track it through time. And at each time instance, we leverage the model prediction from the most plausible model to optimize the treatment for that particular patient. By the way, some of these ideas are coming from our earlier work back in 2014 on basically dynamic data-driven systems. All right, so this brings me to a little bit of future work. I think I can spend a couple of minutes on this, on how these can be extended to neural net. The problem of interest that we recently started is high performance thermal insulation using a mesoporous materials. And the idea here is developing a hybrid physical and machine learning model. I mean, you guys probably seen lots of porous scale models with lots of complexity. Here, I'm just giving a very simple example. If we have a diffusive heat transfer, the conductivity depends on the microstructure indicator or microstructure pattern through the domain, where we have basically our pores, where is the solid part, and so on. And the idea here is that the samples from that microstructure can synthetically generated from a machine learning method that is getting lots of attention these days, generative adversarial network. This approach consists of two networks, generator and discriminator, that in min and max gain sense, they learn the property distribution of microstructure pattern. It's not just microstructure, it uses for a variety of application as well. But the issue with GANs and in general in neural net is that we need large degree of intervention for training, because we look at the training of neural net in a classical sense, in a maximum likelihood setting. Then in GANs, we have mood collapsing. And the main problem that I'm trying to address is that what architecture we should pick to avoid overparameterization, basically, for the generator and discriminator, or in general in a neural net. A generic form of neural net is shown here. It consists of a bunch of weights, bunch of biases, activation function, and what currently we are working on is to come up with an adaptive strategy similar to OPAL, and using Bayesian inference and leveraging evidence for selecting the neural net model. And by neural net model, I mean the architecture, number of hidden units, connections, activation function, and so on, as well as the form of prior and the form of noise model that are extremely important when we are discussing about the Bayesian neural net. So there are many challenges here that comparing with mechanistic models, now we are dealing with huge set of possible neural net models. You just change one neurons, you get different models basically. We need a scalable solution for high dimensional Bayesian inference because of the large number of weights and biases that exist in neural net. And I believe that a systematic architecture selection should be a combination of bottom-up and top-down approach, as opposed to OPAL that is only based on a bottom-up approach. One general framework that we can use for obtaining the plausible neural network models is using a hierarchical Bayesian inference to simultaneously obtain the parameters of neural net, hyperparameters associated with noise and prior, and gives us the architecture plausibility. And in each level, the evidence is the new likelihood for it's a likelihood for the Bayesian inference in the next level that provide us with some machinery for selecting the particular architecture for a given data. Now, this brings me to some final remarks. The model selection in general and the strategies such as OPAL sometimes are mistakenly confused with this code that the complexity of the model should match the amount of data, which means that if we have a lot of data, we need to reside to a simpler model, although we know that those models may not be correct. So this general thinking is the main cause of dangerously overconfidence prediction. We rely on Bayes' theorem, in which the choice of model is a matter of prior belief on the parameters and the model itself. It doesn't depend on the amount of data. Basically, if we are dealing with a complex physical system, we never have enough data, although the data might look big coming from imaging. They're always uncertain and incomplete to characterize the behavior of the complex physical system. The general philosophy for constructing the initial model set, as advocated by these two classical papers, are to include the models that we genuinely believe in, but include all imaginable and trustable model in our initial set, because our model selection approach might end up with a simpler model and may lead to better prediction. The final remarks here is that the OPAL that I presented here are based on certain assumption that works for many of the application, but it's basically a blueprint, and its implementation depends on the computational feasibility of each step in a particular problem, the measure of model complexity, and validation tolerance, and ultimately they are subjective decisions of the modelers for the particular problem. This brings me to the end of the talk. These are the related papers. The one on experimental design of OPAL is actually submitted to CMAME and is coming out very soon. Older paper on OPAL, including Encyclopedia of Computational Mechanics. The tumor prediction is basically a paper that is going to be submitted to IEEE transaction of medical imaging. And at the end, I acknowledge the support of NSF Career Award. And also, I would like to thank my grad student for providing the results here. Jean Gibb did the heavy lifting work on the model selection and OPAL part of the talk. Polly provided her work is on the tumor modeling and a scalable algorithm for high-dimensional Bayesian inference, and Pratiush, the master's student, is working on the Bayesian neural net and generative adversarial network. At the end, I would like to thank you all for taking the time to attend the seminar, and I would like to take any question at this point. Thank you.
Yeah, thank you, Daniel, for the very interesting talk and give us a lot of information regarding mathematics, statistics, and I believe we'll learn a lot from here. So if there is any question from the audience, so please feel free to unmute yourself and ask your question here.
So Daniel, so can I ask a question?
Sure.
Yeah. So first, very appreciate your very interesting talk. So about the second part, you mentioned the optimal model selection. So I'm wondering, when you do the model parameter uncertainty, how to determine the prior distribution of the parameters? So for in some of my previous work, I also wanted to determine what's the optimal model parameter for some problem. But sometimes if I search the parameter, the range of the parameters, many times I found that the optimal parameter is out of my testing parameter range. So is there a way to generate a good prior distribution of the parameters so that you can get the optimal parameter inside the prior?
Right. So basically, philosophically, when it comes to mechanistic-based models, the prior needs to be constructed based on maximum entropy principle, which means that you have historical data, you have historical knowledge about the parameters, and then, for example, modulus of elasticity of the particular material changes between 1 and 10. And based on those information, you can construct a prior, and it can be uniform, it can be Gaussian, and based on the information that you're dealing with. However, in reality, for example, as you said, and it's very true, for example, this strain gradient plasticity that I discussed, we don't have that much of information about the length parameters in terms of prior information, right? Yeah. So it's a very important problem, basically, to construct the meaningful prior. So in the tumor project, we try to bring some information, right? For example, tumor heterogeneity and everything. But this is actually an open question. So in terms of neural nets, we are basically in more trouble because this is not like elastic modulus that we have any information about those before, right? They are just parameters coming from data-driven. A way that can be constructed, and I think these are the way, at least level 1 and 2, has been I have seen in a couple of new papers, including Dr. Kaniadakis' review paper, is that to basically construct a prior and noise model in this hierarchical type of Bayesian inference. But I know that many people are focusing on constructing prior in neural net. That's an important topic.
Okay.
Yeah.
So another question is about the correlation between the model parameters. So, for example, in your example, sometimes you have 4 parameters and 6 parameter, but maybe the 6 parameter there's 2 or 3 parameter they are correlated.
Exactly.
So in your when you select do the model selection, do you consider the correlation between the models?
Sure. Those parameters that are correlated with each other, even though it cannot reflect it in the results that I put in the slides, there are ways to account for those correlation without doing the actual Bayesian calibration, or in the validation set, basically. Our assumption in general is that the calibration scenario is very simple. So we can do it for multiple models. We can see that if the parameters are correlated, how parameters are sensitive, and so on. But the validation is a very complex and computationally expensive. So the way that we, and as I said at the end, that depends on the problem that you are looking into. If you can do the validation ahead of time, why not? But we try to take care of those things, such as parameter correlation in the calibration set. And we pick the most plausible model to do it in validation. Because simply our assumption is that we are not able to do all those analysis in a validation set for all the models. I mean, the problem I said here, it's just 7 models, but you know that in general, it can be 100 models, and we need to test all of those, right? But that's a very good question.
Okay, thank you.
Thank you.
Hey, Daniel. So in fact, I have a question about your strain gradient model. So that kind of remind me some of my previous work. So here, I'm just wondering if you string gradient, you call it SG string gradient model, also needs to follow some kind of yield function?
Oh, yeah. I didn't go that much into the forward model here. But yeah. They follow the yield function, and it's a generalized yield function, right?
Generalized yield
function.
So
Y here is basically our flow stress or yield point. But we also have another size-dependent yield point.
Okay,
right?
I see.
So it's not really that classical that they show, like, I forgot all of those, but like in the 3D space of the stress that shows like a circular and everything. So this is actually size dependent. So I don't know if this figure show you, but you can see when we change the length parameter, the dissipated one, the yield strength changes, right? Yeah.
And also for the numerical implementation of your prediction for the plastic stream, so do you also follow the trial and the correction like algorithm or?
Yeah, but this is basically, I know what you mean exactly, but when you comes to having this term, then probably we just need to use Newton solver, right? To solve these two equations in a coupled form. And it's not very easy when it comes to gradient plasticity. We need very small time step in Newton solver because they are very highly nonlinear. We have Cauchy stress here, we have deviatory Cauchy stress. They are extremely engaged. And I think one reason that people hasn't done as much work on calibrating the string gradient plasticity is because of those computational complexity. We need mixed finite elements. We need to be careful about compatibility of discretization. I don't know if I have it somewhere. Yeah, so all these grains, basically, you need to be careful about mesh size and getting this boundary value development around the edges and everything. So it makes it a little bit complex.
I see. And my second, thank you very much. So my second question is about the page 21. So on page 21, you list a table and show some comparison between different different models, like from M1 to M7, and you have the validation matrix. So here you mentioned that it seems like M4 gives the best validation matrix. But here, so to me, it seems M4 and M6 and M7 are quite similar. In fact,
we are looking at the last column, right?
Yes. How to validation matrix?
Oh, validation matrix is basically here is the DKL, which is a measure between two probability distribution. Between the strain energy that is computed from the model using validation parameter and the validation data, basically the one that is shown here. How much close is these two distribution to each other? So the idea here for advocating that, for example, M4 is doing better because this is slightly smaller, right? And remember that in each of these cases, we are doing different type of data that is designed for that particular model. So my understanding in general is that the calibration process is basically only goal here is to provide prior for validation. And the main prediction coming from extrapolating the validation data to the prediction scenario in which we don't have direct observation, right? So that's why the validation data is very important and we are working on it. Obviously, we can do similar design for the calibration data. We can make sure that those processes are also applied and they are informative. But at least from engineering side of my understanding is calibration data is, let's say, you want to design a big airplane. You can do lots of uniaxial tests, right? those can be leveraged for calibration. But if you are doing a wing of that airplane, validation should be very close to your prediction. Basically needs to have some feature of the quantity of interest that you want to account for. So that's why our validation matrix is at least a measure for us to tell us that M4 is doing better than M6 and M7. Although it's not like much of a difference, but it's just interesting that we add more parameters, we are not necessarily doing better prediction.
Right. That's what I was curious. Yeah.
Right.
Yeah. Thank you so much for the further explanation. So any other question from the audience? So if not, I hope the audience can enjoy the 1 hour discussion and presentation from Dr. Daniel Fagihi. And that's thank Daniel again. And we really appreciate your time and your very nice presentation to share with us. And next week, next Wednesday, we have the we have the similar like CFSM seminar, and I hope more friends can join us next week. Thank you, Daniel.
Thank you very much. Thank you for the
invitation. Thank you, Daniel.
Have a good one. Thank you, guys.
Bye now.